Hello everyone, my name is Artem Molchanov. In this presentation, I am going to talk about Brain Principles Programming, or BPP, which can be used to create a decision support system based on formal mathematical methods. Under the principles in BPP, universal mechanisms for working with information are assumed, which are implemented at all levels of the organization of the nervous tissue and can be determined by mathematical models. What are these principles and how are they implemented in the decision-making process? First, let's imagine we closed our eyes and we have something in our hand, and we need to guess what's that. First, we generate different theories, like it might be toy cube, some ball, apple, stone, or something else. All of these theories are being augmented by different properties, like each hypothetical object is attributed with the properties that it has, like the weight, hardness, size, surface, and shape. Due to simultaneity and relationship principles, these characteristics are perceived at the same time, and different parts of a system form the outcomes and process the theories based on that information to each other. Then, according to the heaviness principle, the theory with the most relevant set of attributes wins. Then we have a kind of decision. We can use approximation to essence principle and approximate a certain apple to some apple, regardless of the color, smell, and actual taste. So we can just tell that that's an apple. And now let's discuss how the brain processes information and what it looks like in terms of basic algorithms and data structures. Suppose a fundamental ontology and basic semantic model of an operational space corresponding to a specific subject domain are initially set. Signals as unstructured data taken to the system, and specific objects of internal graph-based memory are activated. After that, in the brain, the amount of received information is increased due to the existing associative links between objects in memory. It depends on their proximity and frequency of joint activation. Like when we guessed what was in our hand, do you remember? Generation of complexity principles work exactly so. The brain reacts not to an object of reality, but to how it relates to other information in memory. So the evaluation of the generated information is carried out precisely through the correlation of some objects with others. This is a relationship principle. In reality, there are no absolutely identical objects. So the brain performs an approximation, that is, it ignores difference if it managed to assign one or another essence or functional to an object according to specific characteristics. Stable combination of these objects in memory activate objects of a higher conceptual level. Thus, the principles of approximation reduce the number of involved objects and the uncertainty of the system. The brain simultaneously processes the same information in different ways to get several results and combine them into one later. Information from various modalities of perception is also transformed. Actually, the principle of simultaneity or locality distribution provides parallel calculation and transformation of objects. The number of links, relation between objects attribute, ways of calculating information, all these components in relation to the goals of the system determine the heaviness of the final object and final decision of this system. All of these principles work together and in a system and are implemented at all levels of information abstraction, from simplest instances to abstract invariants. So now we will show how it can be described by formal mathematical methods. First, it's a semantic probabilistic inference framework that can be used to make logical inferences on a chain of predicates or relationships within the semantic model of an operational space corresponding to a specific subject domain. This method differs from other methods of causal discovery in that it's maximum specific. It uses all available information, which makes it possible to obtain a consistent set of causal relations. Probabilistic formal concept analysis method builds invariant superposition of object property values. At the same time, It describes statistically reliable classes of object instances corresponding to natural classes of objects within a given subject domain. Unlike metrical clustering methods, this is calculated from probabilistic patterns learned from data using SPI method. And also, very important that this method is fully interpretable, that can help us understand uh, how we get the result. Task-driven approach is used to ground all other frameworks to a specific subject domain, defining its operational spaces in terms of a semantic model, including the success criteria for the task being solved in an operational space. That is, for each of the specific domains where we need to implement a decision support system, we can describe the operational space of a domain in terms of respective ontology, including the goals and criteria for achievement of these goals. Finally, the theory of functional systems bind the success metric evaluated based on real-time operations of a system, relying on all previous frameworks with respect to the goal achievement criteria. The last makes it possible to perform reinforcement learning for any operational space, dynamically acquiring and adjusting behavioral models in interpretable model representation expressed by probabilistic semantic logic. The achievement of the goal, in this case, is predicted and unfolds into a structured order system of sub-goals, leading to the achievement of the main goal. These mathematical methods that can be used to formalize these brain principles and implement them in a decision support system have been presented at the AGI 2021 conference last year, so you can find the details in the submitted publications. Now let's look at how these methods implement BPP in a single architecture in the example. Imagine a decision support system for a sales manager. That system collects events and states for respective business environment and logs them into a database as instances. Those instances are passed to the semantic probabilistic inference subsystem that, according to the generation of complexity and relationship principles, forms the probabilistic rules. These rules are stored in the database and passed to the probabilistic concept analysis framework, which infers statistically reliable invariance out of the activated instances and given rules. Here we can see the approximation to essence principle, acting so the typical invariants are mined out of raw instances. So this is how information is accumulated and experience is formed. At some point, the market state may record the fall of sales. And at that point, the sales manager comes with the question what to do in such cases. We assume that this question is aligned with the corporate goal of probability. So this goal is preset in the task-driven approach framework. The known invariants, according to approximation to essence principle, are retrieved from the database along with applicable rules and directed to the probabilistic formal concepts framework to assess the possible predictions. If some of the invariants contain the recommendations, they can be used right away. Otherwise, extra logical inference is being performed to infer a solution. The recommended solution is being inferred with account to the generation of complexity principle, so all possible scenarios are considered. Every scenario, according to the relationship principle, is considered in relation to each other, to the specific goal, and possible other contextual information. And finally, according to simultaneity principle, all these multiple scenarios are being considered and inferred individually, yet consistently, while the evaluation of the possible outcomes is consolidated across all of them. Based on all possible scenarios, the one being probabilistically assessed as the most relevant for the specified goal given the current state is being selected based on heaviness principle by semantic probabilistic inference subsystem. At this point, the recommendation is delivered to user, while prediction of the state expected upon execution of the recommendation is sent to the framework implementing theory of functional systems. In our example, extension of the product line is the best found solution for given context. So this is given as an answer and corresponding expectation recorded. Expectedly, upon implementation of the recommendation by the manager, the sales actually grow, which is recorded by the new state. The recorded profit is evaluated as success and, according to approximation to essence principle, matched with the other invariants of success story by the theory of functional system framework. The relevance and probability of the rules predicting such outcome increases. With the applicable rules selected according to the relationship and happiness principles, the most relevant probabilistic rules are boosted. So, the positive experience is consolidated. The described flow can be supported with implementation of cognitive architecture incorporating the presented principles with 4 formal mathematical frameworks integrated with each other. The backbone of such architecture will be a hypergraph database capable of keeping both instances and invariants according to the operational environment of a subject domain encoded in the metadata part of the database, along with probabilistic rules binding the properties of invariants. To find out the details, you can see our publications. The theoretical part of our work is presented in the first preprint and will be published in proceedings of this conference, while the practical discussion of application of our cognitive architecture to implementation of practical decision support system can be found in the second preprint. Thank you for your attention. See you at AGI 2022. Bye.